Okay, so we were talking about placing masses on like a seesaw and trying to see whether or not we could get the system to balance. So we were talking about the torque of a mass, just one particular mass about this base. So the torque about the fulcrum looks at the distance, the sign distance from the center of mass, and then the mass times the gravity. So the sign difference, if M1 is on the left-hand side of the center of mass, then its distance is negative. If M1 is on the right side, like M2 and F3, then its distance will be positive. So after we do this, we want for a balanced system, the sum of the torques equals 0. So now this happens to be the torque for 1xk. So, excuse me, this is the torque for 1xk. So let's look at the summing them all. So when we go to sum them all, we get the sum k equals 1 to n. So in the case, if there's one, in our case, we had 3, n was 3, but in general, it can be more than that. And we're going to sum them all up. So we sum xk minus x bar, which is going to be our center of mass. It's a number, times mk, which is the mass of each, the mass of each mass, how much it, in kilograms, and g gravity, because that is the force that's wants to pull it down. And this has to equal 0. Okay, so the first thing I can do is pull g out because g is a constant. So I get the sum k equals 1 to n of xk minus x bar times mk is equal to 0. So I can divide by g on both sides, and therefore g will disappear. Okay, so now let's multiply what's left. So we get the sum k equals 1. I don't know what happened to my n here. That does not look like an n, but now that's an n. And I'm going to get xk times mk minus x bar times mk. This is in parentheses, and that is equal to 0. Now the sum of the difference is the difference of the sums. So I can make this the sum k equal 1 to n of xk times mk. And since x bar is a constant, I'm going to pull it outside the sum, and I get this. Oh, I'll just leave it. That's good. Yeah, that's fine. K equals 1 to n of mk is equal to 0. So let's put that on the other side. So I get the sum k equals 1 to n of xk mk is equal to x bar times the sum k equal 1 to n of mk. Now I want to solve for x bar. That's what I'm trying to get. X bar is what I want. So let's just divide. And we now get that x bar is the sum k equals 1 to n of xk times mk. And that whole thing is divided by the sum k equals 1 to n of mk. All right, so now as you sum the masses, that's easy to see now that that is the system mass. Okay, and as you look at the top thing here, this is the system moment. Okay, so that's the system moment. Okay, So here's an example. So I have a system here. Here is 0. And I'm going to take, and I'm going to put a mass. So this is -1, -2, -3, -4. So I'm going to put a mass here, M1, and it is going to be 100 kilograms. And then I want to put a mass at 2. I'm going to call that M2, and it's going to be 50 kilograms. And then I'm going to put a mass at 4. That's going to be M3, and it's only going to be 2 kilograms. It's going to be a really light mass. Okay. We need to find X bar. Okay, so the first thing we can do is sum the masses. So M is the sum of the masses. Okay, so that's 100 plus 50 plus 2 equals 152. Okay, that was easy. Okay, so now we need to do the system moment. Okay, did I give that a name? Why do I feel like I already said this? Yeah, I did. It's M0. Yeah, I did. It's M0. Okay, so now I'm going to have 100 times -4 plus 50 times 2 plus 4 times 2. And that equals -292. So now I can honestly say here, X bar is going to equal -292 divided by 152. I have no idea what's going on. Okay, so that's close to -2, so -1.92. So that means that right about here would be my center of mass, X bar. Okay. So next we want to find the mass of a thin wire. All right, so this is part B, to find the mass of a thin wire or a rod, whatever it is. It could be a hair. All right, so our goal is to find the center of mass of it. All right, so we're going to do a derivation. All right, so I'm going to get, now you have to imagine that this thing is very thin, okay? So this is from A to B, so it has a length. And I'm going to take a small chunk of it like this. I'm going to find the middle place of it, call it xk, and this length is delta xk. Okay, so that's the little piece, some little tiny piece in here. Okay, so now I want to attach a mass there. So we're going to attach a mass. This is what happened last time. Go away. Delta MK at location XK. Okay, so now I have a mass there. So there's some mass MK that's at this location XK. And I know that X bar is the system moment divided by the system mass. Okay, and so we know that the system moment, we already found that, the system moment is the sum k equal 1 to n of xk. And now I want to multiply it by this little bit of mass. So it's going to be delta mk. So that's a little bit of mass. Now, what do we know about density? Okay, so density, so in 3D, density, which the book denotes as, not rho, that's what I'm used to using. Delta is mass per unit volume. In 2D, density is mass per unit area. But in 1D, density is mass per unit length. And for us, our length is delta xk. All right, so that means then I can take delta mk, so density is the mass delta mk divided by the length delta xk. So now I get delta mk is delta of xk, which, yes, times delta xk. All right. So therefore, X bar now is going to be the sum k equal 1 to n of xk delta mk divided by the sum k equal 1 to n of delta mk. All right, but that equals the sum k equals 1 to n. I have xk, and in the place of mk, of delta mk, I am going to place delta times delta xk. So this is going to be delta of xk times delta xk. And that is divided by the sum k equals 1 to n of delta of xk times delta xk. All right. That's for one little region. Now we're going to chop this thing up into n regions. Then we're going to let n go to infinity, so the length of each thing goes to 0. So now I want to take the limit as delta xk goes to 0, or as n goes to infinity. And you know we end up with an integral. So therefore we get x bar is equal to the integral from a to b of x delta of x dx divided by the integral from a to b of delta of x dx. Again, now, so we end up with this. All right, so I think I just wrote it. Yeah. Okay. Now, if you look at the notation, we have delta m k is equal to delta at xk times delta xk. And so that thing goes to dm is equal to delta of xk, delta of x times dx. So when we use that, we get another formula, which is this one. Uh-oh. So whichever formula you choose to remember, either one will get you to where you need to go. All right, so I'm going to put up some definitions for you. And then I'm going to take roll. Come on now, give me a break. All right, so we have an example. Here's my example. All right, so I have a thin rod that is 10 meters long, which thickens from left to right by delta x given by 1 plus x over 10. Find its center of mass. All right, so this formula gives me delta. It gives me how long it is, so I know it goes from 0 to 10. Here's delta, and that's all I need. All right, so I need to compute m naught. All right, and I need to compute m. And then I can find the center of mass. All right, so these are my formulas. So the first one is to compute m naught. So m naught is the integral from 0 to 10 of x times 1 plus x over 10 dx. And that is the integral from 0 to 10 of x plus x squared over 10 dx. And this integral turns out to be 250 thirds. And that's kilogram meters. Okay. Then we need to find m. That's the integral from 0 to 10 of just the density dx. And that integral turns out to be 15 kilograms. Okay, so therefore X bar is going to be M naught over M. So that is 250 thirds divided by 15. And that comes out to be 50 over 9 meters. Okay, a little bit more than the center. Okay, this is approximately 5.56. So this rod that's getting thicker only by x over 10, not a whole lot, but by x over 10, this particular rod has a center of mass of 5.56. Okay. Now let's talk about the mass of a plane region. And I want to draw this plane region. Okay, so here's my plane region. It's rectangular. It's very nice and easy to work with. Okay, so I want to find the center of mass. Now the center of mass is going to have a X location and a Y location. So here's my center of mass. It's going to have an X location and a Y location. So let's look at any mass that happens to be inside of here. So here's a mass. And this is my mass MK. And it is located at XK, YK. So that's where this mass is. All right. Well, the system mass is easy to find. That says just add up all the masses. So the system mass that's easy. That's just the sum. Oh, that does not look like a sum. That is the sum. Oh my God, what's wrong with my hand today? There we go. The sum, K equal 1 to N of all the masses. Okay, so that's easy. Whatever number the masses are, add them up. Now, when I talk about the moment about the x-axis, here's the x-axis. And the moment about the x-axis is the desire for something to want to rotate about the x-axis. And that depends on how far it is from the x-axis. So the distance MK is from the x-axis is YK. So therefore, the moment about the x-axis requires us to sum up each mass times its distance from the x-axis, which is YK. And then the moment, and we call this thing MX. Then the moment about the y-axis Well, this is sum of k equal 1 to n of the masses and how far they are from the y-axis, which is xk. And we call this my. And so the centroid or the center of mass is the location xk bar, x bar, y bar, where x bar says take the moment about the y-axis and divide by the mass, and y bar says take the moment about the x-axis and divide by the mass. And that's what you get. Okay, so here are the definitions. They'll be helpful to you when you go back over these notes because these notes are posted. Okay. So as we said, the system mass is to add up the masses. The moment about the x-axis is to take the masses times their distance from the x-axis. The moment about the y-axis is to take the masses and their distance from the y-axis. And then the centroid is just x bar, which is my over m, and the y bar is my over m. And then I have an example. Okay. So I want to consider a plane region with the following masses. So I have something that looks like this. Okay, so there's a mass M1 at -2,2. There's a mass at 1,3. There's a mass M3 at 7, -4. And then there's a mass at -3, -2. And I need to find the center of mass, okay? So in order to find the center of mass, I need to first find the mass. All right, so the mass M. All right, so what does that equal? That's 4 plus, come back. Go back over here where I want you to be. Thank you. 4 plus 3 plus 11 plus 1. 19. Okay, so we have a total mass of 19 kilograms. Now, in order to compute M naught, this has to sum up the masses times the y. I'm sorry, this is supposed to be mx. I'm so used to doing M naught. Okay, so this is the masses times the y values. So that's going to be 4 times 2 plus 3 times 3 plus 11 times -4 plus 1 times -2. And that's -29. Okay, so now we need to find my. And that's going to take the masses times the x values. So that's going to be 4. Come back here. Oh, 4 times 2. All right, you come back here where you're supposed to belong, right there. 4 times -2 plus 3 times 1 plus 11 times 7 plus 1 times -3. And that's 69. Okay, so now we can say that X bar is going to equal my divided by m, okay, and y bar is going to equal -29 divided by m. Okay, so therefore, let's see, my center of mass is roughly around 3.6. So I'm gonna just go somewhere around 3.12, 3.6 here, and -1.5-ish. So I would say it's right here. Okay, and notice that that heavier mass has really pulled X bar away from M1, M2, and M4. Any questions? You will have one of these on the exam. No questions? Y'all okay?
Can you scroll back up?
Scroll up.
Yeah.
Okay. To there.
Yeah, that's good.
Okay.
All right, I'm good.
All righty. Okay. 2 more things we must do. That's D and E. The first thing is the mass of a lamina, which is a plane region. Okay. So I'm going to draw a nice plane region. Okay, so this function is going to be y is equal to f of x. So that is some curve. All right, and this lamina right here is my plane region. And I want to find its center of mass. Again, the goal okay, so now X bar, Y bar is going to be a little bit different here. And the reason why is because this has a whole region of stuff with a density that's defined for everything, and it's not just point masses. Okay, so let's find an XK, and then so here's the XK. And I'm going to get a region about XK, maybe not that big. Okay, so here's my, and as you can see, f of xk is right about here. So I'm going to make this thing just exactly that high. And that's going to be an average height for that region. And that average height, as we come across here, is going to be f of xk. All right. Okay, so this height here is f of xk. All right, so now you can see what is the area of that square. So the area of the rectangular region well, that's just length times height. So we're going to call this length delta xk. That's a little space around it. So the height is f of x at k, xk, and then the length is delta xk. And that's just the area for that one region. We can call that AK or delta AK. All right, so that's the area of that little region. All right, so now that I know the area of that little region, let's talk about mass and density again. Remember, M was our mass, nice and simple. But we said that M we took was approximately the sum, K equal 1 to N, of our delta MK. All right, so that was our mass. Now we're in 2D. So that means our density is going to be mass per unit area. So therefore, we're going to get delta at xk is the change in mass divided by the change in area. Or we can say that delta mk, aha, I see something being developed, is delta at xk times delta at ak. So therefore our mass which is the sum, k equals 1 to n of delta mk. In the place of delta mk, I get the sum, k equals 1 to n. Delta mk, I'm going to get delta of xk times my area, ak. But I know what that is. Okay, so I'm doing a lot of substituting here. All right, so the first substitution I did was I said that mk, delta mk, I took this and put that in here. But now I have something even more cool. I already found out what this is. This is this right here. So now I can put that in there and get the sum, k equals 1 to n, of delta of xk. And then I'm going to get f at xk times delta xk. Aha, so I have a nice formula for mass. So mass now is approximately the sum K equals 1 to n of delta of xk, that's the density, my function f at xk, that's my y value, times my delta xk, which was the length of the little tiny interval. And so now, again, we're going to let delta xk go to 0. And n go to infinity. And we end up with a beautiful formula. That is our mass, m. I wish I could write an m real nice. Is the integral from a to b of delta of x, f of x dx. So that becomes our formula for mass. Bam, just like that. Okay. Any questions about that? So now we have a formula for the mass. What we need now is a formula for mx and a formula for my. So we're going to do my first because my is easier. All right, so let me see here. Here's mine. Okay. All right, now let's define my. All right, so I'm going to draw a very similar picture to the one I just had. Not sure how much of this I'm going to get done before time runs out. Okay, so here's my, and I'm gonna draw, I don't know what color I drew it in. I think I drew it in blue. So this was y was equal to f of x. I took a little sliver like this. And so therefore this was delta xk. And over here, this height was f of xk. And then we found an area. Okay, so now let's say I have a mass. And my mass is concentrated somewhere along this line. So let's concentrate our mass. So we want to throw all of our mass right there. Well, it's easy to see the distance the mass is from the x-axis, from the y-axis. And remember, my is the desire for it to rotate about the y-axis. That's what my is, wants to rotate. So we look at the distance it is from the y-axis. And so when we do that, we get my was approximately the sum k equal 1 to n of xk, that's the distance it is from the y-axis, this is xk, times delta mk. Well, we know that that's just going to be the sum k equals 1 to n of xk. Mk is delta of xk times f at xk times delta xk. Okay, so therefore we do the same thing, my now. The limit as n goes to infinity of this sum k equals 1 to n of xk delta at xk f at xk delta xk. And so now we found my. So my is equal to the integral from a to b of x delta of x times f of x dx. Okay. All right, that's it for today. We'll pick up here tomorrow.